In this section, we're going to be looking at applications of second order differential equations. In these videos, we're going to mainly focus on the applications in mechanics. There are a lot of important applications in electric circuits as well. And there are some very interesting analogies between what happens in the mechanics problems and what happens in the electric circuits problems. The information about electric circuits problems and the analogies between electric circuits and mechanics, that information is all covered in the text. In these videos, we will focus mainly on the applications to mechanics. And basically, we're going to start out with a fairly simple situation, which is pictured in this picture here, where we have a mass attached to a spring which can oscillate back and forth. And for now, we're going to assume there's nothing else going on. We're going to assume that there's no air resistance, there's no damping in the spring, and there's no other forces acting on the mass. This might seem like a fairly specialized problem, but it turns out this is a very typical type of oscillation that is really fundamental in a lot of other subjects. Anything having to do with wave motion is going to, including certain topics in electromagnetism and even in quantum mechanics, are going to relate back to this basic problem. But this is the basic problem for now: a mass on a spring with no external force and no air resistance. So the basic physical law is Hooke's law. Here we assume that the force of the spring acting on the mass is proportional to the displacement x, the displacement of the spring from its equilibrium position, x equals 0. We assume the spring would have some natural length, and whatever that natural length is, we call x equals 0. So the idea physically is, if in Hooke's law, the idea physically is if x is greater than 0, so the spring is displaced, k is a positive constant, and that's going to produce a force in the negative direction, which will tend to pull the spring back towards its equilibrium. And similarly, if x is negative, then the force will be positive, pushing it back in the positive direction towards equilibrium. So that's kind of what Hooke's law is all about physically. So to set up our differential equation, we just plug in the only force that we have in this problem, which is the Hooke's law force, into Newton's second law. Mass times acceleration is total force. So that gives us our second order differential equation, which we put in standard form just by putting everything on the left hand side. Mx double dot plus Kx equals 0. And a little bit of notation we'll introduce here. If we divide through by m, we're going to call K over m omega, which is going to turn out to be the angular frequency of this system. So with that notation, our differential equation is x double dot plus omega squared x equals 0. Now we find the solution of that differential equation. That's a fairly simple problem based on material covered earlier in this chapter. Lambda squared plus omega squared equals 0 is the characteristic equation, which has pure imaginary roots, lambdas plus or minus I omega, which gives you this for your general solution. for this type of problem when you have a spring with no air resistance, no damping, no external force. For simplicity and digging a little deeper into this situation, we're going to restrict our attention to cases where the angular frequency turns out to be 1. If the angular frequency is something else, you're going to have basically the same type of situation as what we are going to be reviewing in the next few examples. So in example 1, we have an angular frequency of 1 and 2 given initial conditions, and it's fairly easy to see in that situation that that would be your solution to that initial value problem, and the graph of that looks something like this. So notice the solution makes sense physically if we're starting out with a mass attached to a spring. We have an initial displacement of 3 and an initial velocity of 0. So that means we're releasing the spring from a position 3 units away from its equilibrium. So the spring comes back, initially heads back towards its equilibrium. That's what's happening here. But of course it doesn't stop when it gets to the equilibrium. It overshoots and keeps going, and that's what's happening here, and then until it reaches -3, and then it just keeps doing that, oscillating as a pure oscillation back and forth forever. And that's what we would expect physically in that type of situation, and that's exactly what the analytical solution is telling us. If we change the initial conditions a little bit and leave everything else the same, we get another pure oscillation, in this case a sine type function, and again our spring, physically what's happening here is we're starting from the equilibrium position, but we're giving it an initial velocity in the positive direction. So it starts out moving, physically it starts out moving away from the equilibrium, but then eventually when it gets far enough away, the Hooke's law force, it starts pulling on it strong enough, it pulls it back towards the equilibrium, and then it oscillates back and forth. In example 3, we're still working with a situation where the angular frequency is 1 for the sake of simplicity. This turns out to be the solution of the initial value problem in that case. And here we're starting to encounter the concept of a phase shift. It turns out the maximum displacement turns out to be 5 in this example, and we will look into the reasons why on the next slide. So continuing our analysis of example 3, which we started looking at on the previous slide, we have this differential equation modeling a situation where we have a mass on a spring with no air resistance and no external force. And with these initial conditions, we ended up getting this for the solution of that initial value problem. And in some situations, you may want to leave your solution in that form, but often people will put that type of function in an equivalent form, and the basic ingredients in doing that are in these two boxes here. So we can think of C1 and C2 geometrically as being the components of a vector with angle phi, which is going to turn out to be the phase shift, and amplitude A. So if we just do a little bit of elementary trigonometry in this figure, C1 would have to be A cosine phi, C2 A sine phi. Going back the other way, the amplitude is going to turn out to be the square root of C1 squared plus C2 squared, and the phase angle is going to be the inverse tangent of C2 over C1. So the original expression that we had for the solution was C1 cosine omega t plus C2 sine omega t. And if we substitute in the expressions up above for C1 and C2, we get this. And if we factor out A and use a trig identity on the rest of it, that turns out to be equal to A cosine of omega t minus phi. In terms of example 3, just working out those details in that example, C1 was 3 and C2 was 4. So the amplitude turns out to be the square root of 25, which is 5. And the phase shift turns out to be inverse tangent of 4/3, which turns out to be about 0.927 radians. So this is the original form up here at the top of this slide that we had for our solution, but in some situations it may be more convenient to have the solution in this form where you can see the amplitude and the phase shift, which are both probably going to be physically important values in your application.